Pues sean todos muy bienvenidos a esta semanario, al semanario del Seminario Departamental de CICATA Querétaro del Instituto Politécnico Nacional. Sean muy bienvenidos. El día de hoy tenemos una presentación muy especial. Esta será en inglés. So we are switching languages and start speaking in English. Today we are tremendously honored to receive to Sai Ravela. He is a principal research scientist at the Earth, Atmospheric and Planetary Sciences Department at MIT. He develops succinct data-driven computational methods for natural systems that emphasize the dynamic coupling between phenomenology and physics, simulation and observation, humans and algorithms, and data with models. Current contributions include modeling, inference, uncertainty, quantification, cooperation between autonomous observation of coherent fluids, fluid imaging, animal biometrics, natural hazard risk assessment, and decision support. These contributions are enabled by methodological investigations in machine learning, nonlinear dynamics, stochastic system science, and computational physics. Besides that, I have to be glad that he introduced me to the use of unoccupied aerial systems, the monitoring of natural systems, people's support after a disaster hits, and the dynamic work environment at MIT, for all of which he has a high place in my mind as a respectable scientist and person. So Sai, is truly a pleasure to receive you at the National Polytechnic Institute. And well, now the floor is yours. Thank you very much, Sai, for sharing this time with us.
Okay, thank you very much. I hope you can hear me over there. Just a quick radio check.
We hear you very well.
Okay, perfect. So let me see if I can share my screen, and I will just 1 second, and let's see if we can do that. Okay, so I hope you can see my screen now.
It's coming up, yes.
Okay, so all right, so thank you very much, Professor Salas, for introducing me and bringing me to this talk. I think all of you can hear me now, and hopefully the audio will play. But if there is any issues, just flag me, because as I talk, I can't see your chat box. And I probably don't want to monitor the chat box because it might interfere with my thought process. So just holler and just speak in if something comes up, and we can take it from there. Right. I want the talk to be a little bit informal, partly because the subject is a little bit, I would say, non-standard, but at the same time, I think it's very central to who we are. So today I want to talk about tech for sustainability. You know, this is a huge topic, AI for good and so on. This chart. Oops, sorry about that. I don't know what happened to my presentation. It seemed to have jumped. Give me 1 second. Okay. All right. So this conversation we are having with Tech for Sustainability is kind of taken off. You see it everywhere. And I think this has happened in the last decade or so. And prior to that, there was interest, but there wasn't momentum. And I wonder, and this is a question for all of us to answer, if AI has a savior complex. And this isn't a pejorative term. Saviors can be good, but it's a question worth asking. And I'll present an example of what to do. I offer it as a possibility, not as a prescription, because you can come up with your own ideas for what to do, but I want to put this thought out there. Okay, so one area that we are really interested in is, I want to just go over some work we do. And some of this you're kind of familiar with, I would say. For example, on the left, we worked, and that's near Popocatépetl. We did some campaigns later, and this has evolved. So this project is about using autonomous observation of the environment. And the key theme here is to be able to maximize information gain so that one could observe the environment sparsely, to maximally reconstruct what it's doing. For example, here we might think about a plume of sulfur dioxide that is emerging, and we want to reconstruct it through a very judicious use of resources. The second project that is shown here is a completely different field. It's animal biometrics, where we are interested in recognizing individual animals. And you can see in this particular slide that there are industrial applications. And again, here, there is this notion of relevance feedback from humans. And we want to maximize information gain in asking the right questions of humans. The third project that I'm involved with involves climate change. As you know, tropical cyclones are a huge problem for us. And one of the things we would like to do is to be able to understand the risk from tropical cyclones and floods and so on that are driven by cyclones. And modeling this is not easy because the climate models do not have appropriate resolution. The climate model implement governing equations and of dynamics and thermodynamics. And they don't have enough resolution to simulate these tracks that you see. They don't resolve themselves, so they're not there. So we need to downscale them. It's called downscaling, or you can think about it as super resolution, to produce storms. And if we did that, we would be able to produce risks. So how do we take these future projections and downscale them to produce storms? Requires some ingenuity that combines statistics and physics. But there's also two very important problems. We can think about first problem being uncertainty quantification, because we want to quantify what the uncertainty is in the risk from these extreme events, because that informs decision making. But this is not an easy problem because the dimensionality quickly blows up. And most of you probably know we don't want to do Monte Carlo. So if we do forward simulations, how do we sample the parameter space to drive the right uncertainties? This requires us to solve a backward Kolmogorov equation. Again, machine learning, specifically using informative approaches, maximizing information gain is turning out to be useful. Once we quantify the uncertainties, we have to solve decision problems, where we have to say, well, where do I put the bridge? Where do I put the levee? Where do I protect? How do I? So all these investment or decision choices are available to you for mitigation and adaptation. And this actually takes the form of a stochastic dynamic programming problem, where there are some very interesting challenges, and reinforcement learning could play a huge role. So you can imagine that as the storm passes, we can simulate floods. And this whole system of doing this efficaciously is a huge challenge. Again, the notion of information gain to figure out how to downscale and what decisions to focus on is important. The last but not least, this is a recent project, and I'm going to play this. If the audio is too loud, you might want to turn it down. And this is our, what you're watching here on the right is our ventilator. And this is a test lung. And what you're seeing on the left is the real ventilator. That thing costs $30,000. Our thing costs $300. And it's 90% the same capability. Of course, we are with the FDA now in terms of getting this approved. And we hope to get this sorted out soon. Okay, and there's a startup that's doing this work. And so I would say that these are all areas that we are quite interested in. And now I want to ask you a provocative question, because each of those areas that I've just described to you have a very nice feel to them. You know, they have this AI on one end and social good on the other hand. One is about climate, the other is about environment, conservation with animals, and my God, we're even going to save people. So this sounds fantastic, doesn't it? I mean, like, this sounds like what somebody should be doing with their life. The question is, what's wrong? Is something wrong with this? And at this point, let's just focus it on me as opposed to the field of AI as a whole. And I want to put this provocative question out there because it's worth thinking about, and it shows up time and time again. It's shown up in the past when people were doing certain things in science, and it's showing up again. Let me try to provoke this thought by giving you a dialogue, potential dialogue between me and my son. It goes like this. I'm dad and my son is my son. So I said, Dad says, did you finish your homework? And my son says, I scored 3 runs in baseball today and then 3 up and 3 down. If you know baseball, you know what I mean. I say, well, that's awesome. What about the homework? And he says, I took the trash out too. And I say, well, this is a new you. What about the homework? Then he says, I called grandpa and grandma. And I said, really, when? And there goes the conversation about the homework. This distraction, is something happening here? I think this dialogue may be indicative of what AI is doing. And I will come to this point again in the later, but I want you to bear this dialogue in mind, where an important objective has been traded for other honorable, decent, extremely well-intentioned objectives, but the prime mission still remains completely unfulfilled. And this is a thought that I will come back to again. Okay, so let's take a look at a loose timeline in vision. And I don't mean this to be critical. This is just a particular perspective. It's not speaking for all of vision and AI, but a particular perspective. And it's a quick snapshot. So in 1980s, famously, vision was going to be a summer project. This is computer vision. And it might be sent like it was just as easy as template matching. In the 1990s, we got really saturated by perceptual organization, robot perception, and there was heavy defense-related applications that came up. And the robots obviously are the perfect warriors to drive the AI field. And maybe the thinking then was, well, if the humans can do it, let's just try to mimic that capability however we do it. And there were many good, excellent algorithms that emerged, but still we were nowhere close. In 2000, there was a lot of vision that became low and mid-level vision, not even mid, really low-level vision, and visual retrieval, information retrieval, local features. A lot of things emerged in the 90s and took off in 2000s. And then the thinking was maybe it's all just statistics, like statistics, filters, and flows. Notice that as we are going down this decadal timescale, we are paying less and less attention to understanding computer vision. We're paying less and less attention to really, sort of get a handle on the problem. And we are more and more turning towards a type of problem solving that's not innate to the question. And in 2010, now we started saying CNN showed up. And we said, now we have the opportunity to really train the machine. But remember, the linear part is just convolution. And there was a much more loss of understanding. You can put up with networks now with feedbacks, skip layer connections, residual networks, deep networks, all sorts of activations. And the loss of understanding is enormous. Meanwhile, we are now turning to AI for good. We want to save the planet, remove hunger, help poor people, do great things. What's happening? What will happen after 2020? Where are we going? This is not a critical question it's not a question of a criticism, but it is a critical question to consider. And so I want you to tell me what went wrong. It seems to me that AI needs to find a solution increasingly for others' problems. The only one who appears to be the only one who can help. Where is not AI today? It shows up everywhere. Even your car mechanic talks about AI. But where does it need to be? And this is nothing intended on car mechanics. I love car mechanics. And so where does AI need to be? It seems to be it's everywhere and nowhere, because we still don't understand how this intelligence process works. And we are nowhere near to understanding. I'd say we are losing people who really were interested in that problem. The field cannot extrapolate, cannot generalize it really well. We still struggle with the algorithms and the learning perspectives. It's difficult to explain the methods. Increasingly, it's just a black box. It needs to be in every place. It needs too much input. You name it. There's many, many issues going on with the field, and yet it's perforating, I would say, every aspect of being. I think this is a problem. And maybe big tech is driving some of this, but it's not where we're at. So I'm asking you this question. Do you think what I'm thinking? It's not everybody else that needs help. Maybe it's AI that needs help from everyone else. Just like my son, Sam, needs help with his studies. And so he's talking about everything else instead of his studies. Maybe that's what's going on. And maybe as scientists in this field, I know there's 78 of participants, including me, excluding me in this call. Some of you are probably vision people. Some of you are not. Some of you may be fluid dynamicists. Some of you may be engineers of different kind. But to all of you, this question would be relevant, is that does the looking inward, how much of it is important? I want to pose it. I want to give this forward that I feel that computer vision is where I would focus my attention, has somewhat stopped looking inward. And it's looking increasingly outward to applications. This could be a blessing, but there's enormous danger science because it's not clear what tools it is bringing to the table. As one of my colleagues pointed out, it's a great problem, the AI problem that is, but the implementation is all muddled. And that's exactly how I would like to think about it. And so I want to leave this initial thinking, and maybe at the end we can come back to this discussion. And to just put a loose timeline, my own personal timeline, green is me, orange is the field. In 1990, I was really amazed by the AI problem, right? And by 1995, all I could think was, how do we see? How do we see? And that's days and nights. I was thinking about what features to use, how to worry about deformations, what happens to occlusions, what happens to, and anybody who's really been in the field of vision has been sweating this problem for as long as I know it. It vexes us. It pains us to see that this obvious thing that we humans do so easily appears to be such a challenge. And by the time 1998 rolled around, I decided this is a too complex a problem. There's something I'm really deeply missing. In other words, I don't understand complexity at all. And all this phenomenological, anthropogenic, anthropomorphic thinking that was in the field was simply throwing me off. At the same time, I was influenced by sustainability-related applications where complexity plays a role. So to me, it was obvious on the methodological side, I need to do something else. And I need to come back to the vision problem. How do we see after preparing myself? And so by 2010, I was enmeshed. I moved in 2002 to MIT. And by 2010, I was enmeshed in stochastic systems and stochastic processes and system science in general, worried about inference challenges for complex systems. And then the applications were open, whether it was climate or dynamics or robotics or vision. And you've heard the introduction that Joaquin gave about me. It seems like a broad buckshot. It's like this guy does everything. And it really is the application, but the methods are quite small. So by 2010, I established some sort of clear methodological basis. And by 2020, I am quite happy with what I have learned. And now I am pivoting to asking a different question that will kind of be the subject of my talk today. Meanwhile, I'm seeing the AI field somewhere around 2010 or slightly earlier has been taking off towards the directions of sustainability. In other words, looking outward, just as I did, I think, around 2000. And maybe it will come back to look itself inward. Maybe this is just a phase shift. I don't know, but this is the comparative way I'm thinking about it. I think that we need to come back to the question of AI. And I think that in so doing, as I mentioned in my abstract, in so doing, we will do the best even for the planet. And let me try to tell you how in what follows. Okay, so the way we're going to idealize our thinking is this space I'm going to call informative learning systems. Going forward, my talk is going to get exceedingly technical, and it will demand that you gain, if you stay up with me in certain aspects. And I will also switch to a presentation where, with a recording. So that way we can all keep track of time. So here on the left, I'm going to show you a fluid simulation. For those of you who've done it, it's very classical. It's the vortex street being produced. And this is an idealization just to get us thinking. And the black and pink dots that are moving around are sensors that are taking measurements. Some are Eulerian, just scanning back and forth. Some are Lagrangian, tracking the coherent structures. And what they're doing is optimizing an observation plan so that the reconstruction of this fluid defined in this XY space can be optimal. We are using sparing resources. In this process, there is a prediction, there's an uncertainty quantification, there is this notion of optimizing information gain to decide when and where to place observations. And there is the option, or there's the process of using that information gain to then ingest back into an estimation process that produces perhaps new initial conditions, new parameters for the model, and so on. So this is our thinking in a system sense. What we are going to do is to turn this process to learning systems. The only difference between this system on the left, which is a fluid dynamical system, and the system shown in the middle is that it is a learning system. In fact, what we're going to think is as follows. We're going to start with governing equations that we kind of know. And then for detail that is not missing or for certain imperfections of this model, we're going to augment it with a learning machine. Think about it as a neural network. Then we're going to think about the dynamics of learning. We're going to think about how learning happens and how it is a stochastic process and how that learning happens and how to control it. With that, we will optimize the learning machine, and together the physical part and the learning part will accomplish certain objectives like predict, improve prediction, or improve observation. And my own interest really is in building observations. Ideally, I would like to observe everything and disturb nothing. So I'm interested in building observing systems for our planet. And this obviously is an important subject, but we are really going to turn the science of stochastic systems and processes to bring to bear on learning itself. Okay, so the outline going forward will be we're going to talk about an informative systems paradigm. We're going to talk about the stochastic learning system dynamics. We're going to introduce informative learning and use that to optimize the learning process. And we're going to apply this to a special kind of problem, which is to discover dynamics from data. In other words, there's data out there that's coming in, and we want to produce equations from this data of a dynamical system that the data represents. That's the problem we're going to apply to. There's been some interest in it, but we are going to come up with an interesting way to think about it. So from my initial discussion about AI, what I am saying is we are going to pivot. Whereas the rest of the world is thinking about applying machine learning to system science, we're going to turn around and apply system science to machine learning because of this belief I am proposing here today that really it's AI that needs help. And of course, once we do this, we can come back and influence all the applications I've talked about in the beginning, but methodologically speaking, this is where we are. Okay, so let me see if I can't start to play this slide by slide. The applications that I have just described can be methodologically framed in a standard systems paradigm. The word systems, of course, is being used a little bit loosely to include a broad number of areas such as estimation, control, planning, decision theory, etc. This paradigm consists of a dynamical system of some sort, usually a discrete dynamical system, and the model F as shown can be specified, or in our case, as we will do in this talk, learned in some fashion. The states are denoted X, controls or external inputs or forces are denoted U, and the model parameters are alpha. We have also an observation equation H and a set of goals G. The standard systems problems pertain to inference. These include a filter, a fixed point at initial time, a smoother, parameter estimation, and the controller. These are standard problems I want to emphasize, though the probabilistic way in which we have written this as an inference problem is a bit non-standard. Methodologically, in science and engineering, for example, F might be a fluid dynamical model with a million grid points. The equations may be highly nonlinear, even chaotic, and the observations may be sparse. We don't observe the Earth everywhere we possibly can't, and they may be noisy. The distribution associated with the state, the probability distribution associated with the unknown state variable, could become highly non-Gaussian. So solving these inference problems is quite difficult, especially if they must be done in real time. But we have to solve these problems, whether it is to figure out how to build an observatory, whether it is to figure out how to downscale, or whether it is to figure out how to numerical weather prediction. There is a sort of systems paradigm that underpins some of the problems that I have talked about in the previous slide. The applications that one way to idealize the solutions to the problem that we just presented in the previous slide is shown in this figure. And I just want to point out that it is common, this approach I'm just going to describe is common to numerous problems in engineering and sciences. I urge you to have a look at the handbook cited on this slide for those applications. Okay, so anyway, the loop begins with, in our case, a theory on the left-hand side. These could be governing equations that were derived from Navier-Stokes, for example, and then follows the blue paths. Numerical modeling is often used to produce high-fidelity models, which must then be reduced for real-time use, and in many cases, just to even make the simulation tractable. The result of this is that predictions have uncertainties. The standard approach to deal with this problem is prediction and correction. Many of you know this as the Kalman filter, or you might have used the particle filter, and the numerous variants in between. This involves using the data and predictions to recursively estimate the model parameters and states, or the reduced model variables, even the reduced model basis. In this standard loop, learning is increasingly of interest, particularly because model reduction leaves out detail that the data still has, and uncertainty quantification remains difficult for high-dimensional problems. In the learning systems, augmentation too, theory may be used, for example, to synthesize the structure of the learning machine, for example, the neural structure, and loss may incorporate dynamical constraints. Unfortunately, the coupling between the physically based and data-driven not sure what is going on, but I just want to point out that the coupling between the two is anything but trivial. It's a really hard problem. To tackle the problem, we will turn to a different idea. In recent years, a kind of active paradigm has emerged in systems using information theoretic foundations. By contrast, the classical paradigm contains a closed loop, tracing the black arrows in the figure shown. It passes through model prediction, uncertainty quantification, and information fusion to combine data and models. Informative approaches augment the dotted lines with an additional feedback path shown in green that maximizes information gain for a variety of purposes, such as observing sparingly but strategically, selecting key input data, selecting key model parameters or states or control inputs, or optimizing the structure of the model itself to prioritize the fusion or update. As we have suggested, many applications have shown that doing so leads to efficacy, especially problems that are nonlinear, high-dimensional, non-Gaussian stochastic processes. For hybrid systems involving data and physics, this is particularly valuable as it allows learning by the data-driven part and estimation by the model-driven part to jointly and stably coexist. And both these processes can be jointly controlled using the same paradigm. Of course, I want to point out that the use of information gain for variable selection is not new and has been made common by approaches such as informative planning, informative sensing, and informative estimation. These are part and parcel of the same paradigm. But what is even more remarkable is how little the informative paradigm has been developed in learning itself. You know, after all, the learning process is high dimensional, nonlinear, and leads to non-Gaussian uncertainties, and it can be thought of as a stochastic process. So there are several ideas within machine learning itself, including active learning, relevance learning, model selection, structured learning, among others. The informative approach unifies these paradigms. At the same time, the proposed approach, informative learning approach that we are going to present, has, to the best of our knowledge, not been shown before, and as we shall see, appears to offer some benefits over sparse optimization paradigms. And we'll see the connection between the two, then the sparse optimization paradigms that are currently in vogue. So to treat the ML audience here, we apply the informative approach to optimize the dynamics of learning itself and show that this makes the learning process more efficacious. To demonstrate this, in the remainder of the talk, we will focus first on the dynamics of learning, then derive the informative learning approach, and then apply it to a particular problem, which is to learn the dynamics from data. As an example of what types of benefit we derive, consider the example shown in this slide, where we are interested in a hybrid system that is part physical, part data-driven. The idea is that we want one dynamical system, let's call it FL, which is, let's say, low resolution, to learn details it cannot normally represent from a high resolution model, FH. This is also studied as a parameterization problem. So once the machine FNN is trained from perhaps simulations of a physics-based FL and a physics-based FH, a high-resolution model, training a low-resolution model, we may imagine that we'd add in the FNN component and somehow thus have a functioning hybrid system that mimics the behavior of the high-resolution system FH. Unfortunately, irrespective of the learning machine used, and this is an important point, if the training is offline, then things won't work because the injection by the learning component simply causes divergence. This is shown in the animation on the right, where the advecting low resolution blue curve is to be augmented with detail that is in the dashed blue curve. The naive strategy of constructing the hybrid simply falls apart, as the brown curve and its axes show. When errors grow exponentially, such as for chaotic systems, this is an even bigger problem. So what can we do about it? If the estimation of FL and parameters of FNN were dynamic and data-driven, then we could estimate and learn jointly in a lagged manner, which would solve the problem as the second animation with the machine ML1 shows, where the first ML0 machine fails. This type of learning of neural dynamical system is feasible through informative learning that we've just described and is an application we are interested in. Another problem is to learn the dynamics from data. Let's be clear what we mean by this. There is some dynamical system that is producing data, and this data will be discrete in time. In other words, it's not a continuously available solution, but it's in discrete time, and it's probably noisy. And what we want to do is to learn the dynamics. In other words, we want to give out the equations. This is the holy grail. I mean, forget model reduction, forget parameterization. If you could stick a sensor out there and out pops the equations, that would be of joy to the dynamicist, to the system scientist, to the machine learning person. This is the perfect, you might want to say, problem to be working on. So we'd start with an ab initio model, scratch, nothing, x dot equals to 0. And through the informative approach presented here, we will arrive at the correct model. Of course, we'll try this on a simple problem first, and we'll arrive at that model faster than we might do otherwise. We will show that the informative paradigm adds the kick, provides the efficacy. And this problem will be the main subject of this talk, in contrast to the stable hybrid problem, which for time limitations, we might not be able to go into, but I am giving another talk at AMS, which will be the focus of that subject. But I invite the viewers to discuss both of these applications with us. For either problems, we want to and will investigate learning as a dynamical system. In other words, we will begin with a description of the dynamics of learning, which allows us to solve for these type of problems using the informative paradigm, and which we argue is efficacious. So with this, I hope the overall motivation and methodological lay of the land is set. And I will now turn to some details towards the development of the informative paradigm with application to learning dynamics from data. Our proposed methodology begins by considering the neural network, which we may normally write as a monolithic function as shown in equation 1. It consists of the input x0, the output xn, and parameters, which represents perhaps weights and biases. We may also open this up to reveal a multi-stage process proceeding from layer to layer. So here in equation 2 and 3, we express classical feed-forward and recurrent networks for an n-stage process. We include the training output as a noisy observation at the terminal stage to model label as well as network imprecision. Feedback and feed-forward components are presented in the standard system sense using the term U and require additional equations for closure. For example, in the top figure, we show a multi-stage process model of the neural network with feed-forward and recurrent components. Another class of system that is more familiar to us is the dynamical system. Here shown in equations 4 and 5 are an autonomous system with constant but unknown parameters, no process noise, and observations with errors. The interpretation is classical, and we consider such representations later in the talk to model neural dynamical systems, which are systems that are described in part as neural networks. Thus, we commence with a systems definition of the network as a multi-stage process, and that of a neural dynamical system, where the process is at least in part a neural network. The system's representation immediately provides the basis for learning as a parameter estimation problem, as shown in equation 6. The performance index minimizes the error norm between the network prediction and training output, respectively xn and yn, and it's adjoined with multi-stage dynamics. You should recognize this immediately as a two-point boundary value problem that's common to a vast number of inverse problems. The normal equations in 7 through 11 reveal the familiar forward-backward algorithm, also known as the adjoint method, 4D var, among many other names. But this is exactly what backpropagation is, though ironically, the original Rumelhart et al. Paper does not mention this result, found in Bryson and Ho's optimal control book much, much earlier. From the forward-backward pass, we obtain a parameter gradient, and many methods from gradient descent to semi-Newton methods could be applied, and this is then just a classical optimization problem. So what's the big deal about writing equations this way, you might ask? Well, three things. First, there's no mystery behind backprop. We know it. We know these equations. But we also know many other things, such as finite time Lyapunov exponents, which we could now bring to bear, say, on the aerodynamics of the adjoint equation and beyond. There are many other problems where it could be applied, perhaps in the design of better networks. So this is just an ideation or an idea we're putting out there with no support in this paper. But this is just to say that there are many things that can emerge by bringing learning into the standard frame. Furthermore, and this is what we do here, if we consider that the gradient is calculated for a mini batch, then obviously gradient descent becomes a stochastic process. Well, this could then be expressed as an Ito equation, whose Fokker-Planck equation describes the evolution of the distribution of weights alpha in time as the network perhaps converges, implying that learning has occurred. Now, we present the details of the stochastic formulation in the archive paper cited at the bottom of this slide, but we omit further discussion here, except just to note that the Fokker-Planck equation immediately leads to the ensemble approach, but this is also well known.
This is perfect, however, because the ensemble approach provides a uniform basis for informative learning, which is what we explore in this paper.
Let's trace the stochastic process argument one more time. Let's start by looking at the gradient descent shown on the top left. We can, to be sure, also derive what we're about to discuss for other iterative approaches, but we just do it for gradient descent here. So on the top left, we have gradient descent, which we have written for a mini batch. And this is written as grad j bar. And once we get this, we can write grad j bar as a perturbation over the whole batch gradient average. So the whole batch average is mu, the perturbation is w, and this depends on the weights or parameters alpha that are changing over iterations. Now, if we model w as a stochastic process, and because it's a perturbation, it's zero mean, and it has an expansion, and you can write a KL sort of expansion for it. And all we've done here is use a Gauss-Markov process. So from this Gauss-Markov process, we immediately can substitute back to derive an update equation in the continuous limit, d alpha t, for the continuous evolution of weights, known as the Ito equation. This equation may also be written in Strantanovich form, but this is easier this way. But notice that this is not the Langevin equation. Don't confuse this with that type of learning. What is happening here is we've written an Ito equation with a drift and a diffusion process. And this has an associated Fokker-Planck equation that allows us to describe the evolution of the probability of the weights, or P alpha. So dP dt describes the partial differential equation that tells us how the distribution of weights evolve. And so if we have a learning system that is undergoing gradient descent, the gradient descent, because of the use of mini batches, turns into a stochastic process, which we have characterized by its Ito equation, which has an associated Fokker-Planck equation that tells us how the uncertainty evolves. From a stochastic systems perspective, this is really just standard. I've just described one part of a class to you, but from an ML perspective, I think this opens doors. I know there are people who are looking at this, particularly Tishpi's group et al. And there are people who've looked at this, but I think this perspective is still not well developed. The beauty of this approach is, for example, that it allows us to think of stochastic optimal control to optimize learning. One simple idea could be to optimize the mini batch size by controlling the dispersion of P alpha over iterations. So although the notation here might seem complex from a dynamical systems perspective, there's really nothing new. But from a machine learning perspective, it could be quite interesting. So what would knowing the equation for P alpha give us? I mean, what does the Fokker-Planck give us? A lot. A lot. For example, the mutual information between the data D and the parameter random variable A can be used to characterize the efficiency of information transfer. Did you just build a bogus machine, or is your neural network really good at transferring information from the data to its internal weights? This can be quantified and perhaps can be maximized, right? The mutual information between data and prediction errors can be used for input selection. Similarly, we can perform parameter selection and structure selection, that is, how to reshape the neural network by adding or deleting nodes. All this can be done. These optimizations will require work, no doubt, but nevertheless, the framework is now there. We have a very clean stochastic process model. We have a very clean Fokker-Planck model connecting with a lot of physics, and we have this notion of information gain, I, that we can optimize. And as we shall see, the use of information gain for selection is also a sparsity promoting optimization paradigm, but it is based on entropy, which, as we've shown, is a much sharper approximation to L0, which is the true sparsity problem, than L1. It is also fully aware of uncertainty, which L1 is really not. So this leads to a greedy sparse optimization approach that is much faster than L1, offers competitive if not better solutions. All this is to come, but for now we can imagine these benefits here. Okay, so all this theory sounds fantastic. And the question is, well, how are we going to use it? Most deep learning happens without uncertainty quantification at all. Every time you go in there and do backprop, you don't get anything back. No pun intended. Even when Bayesian approaches are used, including Bayesian optimization or say variational Bayes, it's not really tractable in such high dimensions as most deep networks live in. And here we're talking of Fokker-Planck equations and characterizing mutual information with them, which appears even more ridiculously impractical. Luckily, we have a tractable approach that is also known as the ensemble approach. This simply consists of sampling an ensemble of parameters, solving the forward equations, in this case a neural network, then evaluating the prediction errors and statistically calculating the adjoint for a parameter update. Now, the statistical calculation of the adjoint is through samples, and remember how to take a gradient by sampling. And this idea has been applied to filtering and smoothing problems, where it is known as the ensemble Kalman filter and smoother. For the filter, here we show an example of estimating the state of a chaotic dynamical system just to give you a sense of the cadence. Between observation, the error grows. Then when the observation hits, it shrinks. The important point here is that there is no linearization of the forward model F between this prediction correction cycles. This is not the extended Kalman filter. This is not for a linear problem. The model F is fully nonlinear. Yet we are not stuck in it, and we are not stuck in a terrible sampling regime like the particle filter. There is propagation and update, which can be very compact. The update is just sort of like a message in a graphical model. Please see the reference for more details of tractable smoothers and other ideas. So what does this mean for learning? Sample the weights, make the prediction, update the weights in parallel. There is no backprop, gone. We have uncertainties of weights available. We can quantify and maximize information gain. And so this is the ensemble Kalman learner, a simple yet highly practical and effective approach to learning. Much simpler than variational Bayes or Bayesian optimization, but convergent to backprop. Extensions of this idea to non-Gaussian problems with mixtures and kernels have also been done, and the citations are here. So next we'll hear from Gabriel, who implemented this for deep learning.
The ensemble approach uses perturbations of the parameters with mini batches of training data to arrive at an update rule similar to the ensemble Kalman filter. Using the definitions of variables shown in this slide, the update to the parameter ensemble matrix A sub I at iteration I using matrix M is weakly nonlinear. We note here that other loss functions, including, for example, mutual information or optimal transport, are also admissible in the ensemble framework, as are other distributions controlling the parameters or targets, such as mixtures and kernels. We've shown this form here for the simple reason that it is easy to understand and offers a direct alternative to backprop. We also note that the ensemble approach to learning is receiving some attention in the literature. However, the results, as we also saw initially, were not that great until we started applying an adaptive version of the filter. In our version, the tolerance with which the label or target is matched is adapted over iterations. As we shall further see, coupling with information gain truly turns this approach into a valuable method. The ensemble learner, defined in equation 14, updates parameters in parallel. There is no backpropagation. So, this removes the sequential back and forth. Thus, this approach is also in stark contrast to variational Bayes, a popular but relatively quite expensive form of Bayesian learning. The ensemble Kalman learner also quantifies uncertainty. As a result, the joint distributions of key variable pairs, such as errors in parameters, errors in training data, or errors and new structural terms, become available. These distributions can be used to quantify information gain and optimize it for a variety of objectives, as we shall use for learning dynamics from data. A first example of the application of the ensemble common learner is to the Boston housing dataset, which is a relatively small dataset. We refer you to the paper for the network structure and dataset details. The ensemble learner converges at a faster rate and more smoothly while estimating the parameter uncertainties. Please note that in the right graph, the initial parameter uncertainties are small, but this is the case of a high bias but low variance. The total error is still large. As the training proceeds, the test errors indicate a lowering of the test error as well as variance. The costs are competitive, if not better than, backpropagation. A second example of the application of the ensemble common learner is to the MNIST housing dataset. We refer you to the paper for the network structure and dataset details. The ensemble learner converges competitively and more smoothly while estimating the parameter uncertainties. Please note that in the right graph, the initial parameter uncertainties are small, but this is the case of a high bias with low variance. The total error is still large. As the training proceeds, the test error indicates a lowering of the test error as well as variance. Again, the computational costs are competitive, if not better than, backpropagation while quantifying uncertainty. Kindly refer to the paper for details, including access to the implemented examples.
The ensemble learner allows us to maximize information gain for a variety of objectives. We maximize for variable selection in this paper, which is an L0 problem. The objectives may include parameter selection, such as in a resource-constrained setting, input selection, for example, to turn big data into smart data so we're not evaluating all the data, structure selection to optimize the structure of the model, among many other possibilities. So suppose we had two random vectors represented by their ensemble matrices. Here we're going to use A for parameters and E for the network prediction errors. We can then quantify pairwise mutual information between the random vector components, which we do here by assuming Gaussian distributions. The pairwise mutual information psi ij between vector elements ai and ej can be sorted. Again, to information selection criteria that's quite popular in machine learning, especially the old style machine learning, penalizing the number of terms selected against the expected increase in information, we arrive at a greedy solution to the L0 problem, which produces a subset of A terms, or if desired, the AE pairings that we are going to select for subsequent use. The greedy L0 problem approximates an NP-complete problem, but it can outperform solutions to the L1 approximation like lasso, as many people have shown. In addition, the greedy solution can select terms ab initio, which is better than, say, Monte Carlo, and better than many versions of, say, MCMC. It is also better than variable elimination from, say, a large initial set, for example, using L1, where elimination occurs when the weights of the parameters are driven down to very small values over iterations. So this approach involves no iterations and is both memory and time efficient. It's a simple greedy solution to an approximation to the L0 problem. And the use of information gain allows for that. It can, in fact, serve as the maximizing information gain part to the ensemble learner so that in a coupled manner, they can solve problems. And this can be done with or without lasso-like constraints. This, of course, is at the heart of DDDAS and leads to the new informative learning paradigm. We now turn to the application of the informative learning paradigm, which couples the ensemble learner with maximization of information gain. We pick the structural learning problem, which is to estimate the structure of the neural network and its parameters. In particular, we are interested in neural dynamical systems, which, as we've described, are systems that are in part described by neural networks. What we want to do is to learn the structure of f of x in the dynamical system x dot equals f of x when we only have noisy discrete time series data, x1, x2, and so on. Unfortunately, this is a very difficult problem. It is difficult to assess structural optimality without knowing ground truth, but if the ground truth were equations, it is still very difficult to interpret the neural network in how it matches those equations. Of course, the use of learning brings generalization problems with it, and we can say very little about extrapolation. So it's not trivial, other than in some simple local sense, what structure was learned for the neurodynamical system. And to overcome these issues, We restrict the problem to a special but broad class, nonlinear dynamical systems with polynomial dynamics. Such systems are increasingly of interest for several reasons. First, in continuous or discrete forms, they have exact neural networks. This means that learning the neural representation correctly reveals the dynamical equations, or in other words, we would have learned the equations from data. There is much interest in this version of the problem, that is, how do we learn the dynamics from data? However, to be sure, we are interested in the general problem of structured learning using informative neural ensemble common learning, for which this use case is great validation.
As an example, consider the chaotic Lorentz 63 system of equations, which contain a quadratic nonlinearity, as shown in the left figure. The discretized version of these equations, say using a Runge-Kutta fourth-order method, has an exact neural network, as shown in the top panel in the middle. In other work, it has been shown that compact recurrent neural networks exactly implement both Runge-Kutta and Adams-Bashforth-Moulton schemes. In fact, they are exact for a large class of explicit and semi-implicit methods. Embedded within the RNN is a polynet, which is the exact neural network corresponding to the polynomial equations, as shown in the bottom panel in the middle. This representation contrasts with other work in the sense that our neural representation of polynomials is exact. These networks are constructed trivially from the equations themselves, and thus we have discrete time neural dynamical systems. As the right figure shows, the neural and numerical simulations are identical, but for floating point error at 10 to the negative 16, which, as the equations say, will also grow chaotically. So if you want a neural network for the Lorentz system, just compile this and run it on a tensor core. Thus, we can perform structure learning problems on a numerically simulated version of the Lorentz equations, using the simulated data to train the polynet scheme we have just described. From the network recovered, we read out the equations to reveal what dynamics we learned. We have to be clear that the training data will be both noisy and discrete in time snapshots, although in our experiments the noise is quite small. One way to solve the structure learning problem for the Lorentz system is to start with many polynomial terms, shown here in the orange panel by variable x. Then we can use ensemble common learning in the normal manner described earlier for parameter estimation. We perturb the coefficients associated with these terms, which are the weights. We use the ensemble common equations to update iteratively from a mini batch of data, which are short perturbed simulations from an initial condition. In the way we do it, it is not even guaranteed that the ensemble perturbations are on the attractor. Nevertheless, we stop parameter estimation when there is no further improvement to the error or error variance. Along the way, whenever a parameter's coefficient is close to 0, we remove it. This way, we recover the correct Lorentz equations, but after many iterations. This experiment is also a little too good to be true, in the sense that all the correct terms are in our original set X, and we haven't confounded it with too many. Still, it takes too long. We apply the informative ensemble common learner in the second approach. This one is difficult. We apply the informative ensemble common learner in the second approach. This one is difficult relatively in two ways. First, we start ab initio, that is, x dot is 0. We know nothing. Second, there are no particular bounds on terms that could be selected. We then make predictions, which is persistence for a parameter ensemble, and then maximize information gain as previously described. This gives us terms, and we then proceed with ensemble common learning iterations, stopping when variance cannot be reduced, eliminating terms with close to 0 coefficients, then repeating. The correct equations are recovered quickly and much faster and in only 1 or 2 term selections. Thus, the coupled information learning and parameter estimation process, a DDDAS principle, efficaciously recovers the dynamics from data. This chart shows the terms on the x-axis and the ensemble common learning updates on the y-axis. Terms selected at any point during the algorithm are in blue and green, the blue ones being terms rejected by greedy information gain maximization. The final surviving terms, which are in green, are the correct terms. These two charts show convergence. On the left is the convergence of coefficients with 10 to the negative 4%. And on the right, the variance of the surviving terms converge. Please note that between variable selection, indicated by the dashed line, the parameter variances of the new terms are rescaled when they are first added. In conclusion, we think the days of backpropagation may be numbered. This is especially true if we want to leverage parallelism and quantify uncertainty.
So I think I will pause here because I believe we might be out of time, but I want to bring the discussion back. What we saw in this talk was we started by applying stochastic systems model to deep learning. Within few minutes, we kicked out backpropagation and replaced it with something simple without jumping into its like Bayesian deep learning in this most general form. And we then were able to use that to quantify information gain, which we turned into a sparsity promoting optimization problem to optimize the structure of the network. We then said that for certain classes of problems, the structure of the network reveals the equations. And if you gave me the equations, I can compile the network directly, immediately. Previous to this, learning polynomials was considered really hard, and there are papers that show that. But actually, it's not. And so that means that if you were to give me data from such a system that had polynomial dynamics and the data was discrete, you could apply the scheme we just did. And once the network is learned, you read out the network, and those are the equations. And when we do this, it is much better than the non-informative approach, much faster. And we can start ab initio. You don't have to start with a large number of terms like Cindy and others do going forward. So I would say that to me suggests that just a simple system science application, which is very vanilla, has helped us gain an insight into learning that was previously missing. So I shall stop here, and maybe for those who are here, we can take some discussions. I know we started out fairly broadly, but we dive deep into a particular example of what I meant by giving AI some attention. And you may have questions both on the specific methods or in the more general scheme of the discussion. And there's a bit of a disjoint between the two, but I hope that we can still have a discussion about it. Okay.
Thank you, Sai. Thank you very much for your talk. Just to give a little bit of context, backpropagation is the cornerstone of artificial intelligence these days, and is the support of all the applications that we are currently seeing out there. So we have a couple of questions. Martin Nieto is asking, how are these machine learning techniques related to the quants, which are now so popular in finance system for market behavior prediction? Are they related?
Could you just say that question one more time?
How are these machine learning techniques related to the quants?
Oh, okay. So quantitative finance, you mean like the quant people.
Right.
So, the quant people, ever since Black-Scholes and so on, have really gone into stochastic processes. They've really mastered it. They have looked at methods from stochastic processes. And so what we are proposing from a stochastic systems perspective could be considered as bringing some techniques that perhaps people in quantitative finance know, which of course I would say has its background in physics and stochastic systems, which they know that we are bringing to machine learning. But the question really needs to be the other way around. How much did machine learning know about stochastic processes? Not much. And that's how this is valuable. But I would say that as a result of my talk, one could say that they are related, particularly because we are stopping to look at machine learning as this separate novel piece on the side, but thinking about it as just another system with a peculiar dynamics that emerge from parameterizing the problem as a dynamical system. So there are two parameterizations. You can parameterize the neural network as it's a multi-stage process, or you can parameterize the learning process as a dynamical system. One is in just a discrete multi-stage process in nodes and layers. The other one is in the iterations of the updates that are happening to the weights. Both are dynamical systems that we are considering that we apply this to. So yes, I would very much say quantitative finance techniques could be brought to bear on either one of those, but I think those techniques themselves borrow from system science heavily. So I would say that the root or the mother of these might be more in system science than in quant per se.
Thank you, Sai. Now from Alejandro Gomez, in information gain, data selection looks like a useful technique, but how to assure that the selection pipeline has no bias or hide some important features?
So this is a matter of prioritization. We don't ask the question to partition between all the important ones from the unimportant ones. We ask the question, how do we prioritize the learning, which is a different problem. And you're penalizing the cost of doing the computation against the benefit of selecting a feature. And this is implicit in the sort of notions of variable selection that we are looking at. It's actually a very old idea, right? Akai-K information criteria, Bayes information criteria, model description length. All of these are based on similar ideas. So when you talk about bias, there are two things to consider. First is that there is an incremental set of variables being added each iteration, each time. That addition process doesn't proceed by variable elimination. It doesn't start with the full set and removing the variables. It starts with a small set, then deciding which ones to add in. But that process is repetitive. In other words, if a variable was missed, it could be brought in later. And if a variable was selected, it could be dropped out later. There will be questions about whether this converges or not. It seems to be actually converging quite fast, although it's just a greedy process. But insofar as the selection itself is concerned, there is no iterations. So to prevent bias, we let the process converge and see whether the variances are reduced. That is, so a variable that has high mutual information will show up in the current iteration. A variable that may not have had a high mutual information may have a high mutual information in a later part of the selection, in a later set of iterations, and it will show up. So instantaneous selection, like at any point in time, maybe you're at the selection step, you look at your prediction, you look at the remaining terms, you calculate the mutual information between them, you sort them, and you decide I'm taking the top 3. That's a decision you've made. You can say I take the top 5, top 10, and so on. So we are parameterizing the cost of the model complexity against the gain that we are getting for the terms selected. And this is standard. So by tuning that, you can, but you don't even have to tune it in the problems we're looking at, because if a term was ignored in this cycle, it could be picked up in the next cycle eventually. I hope that answers the question.
Thank you, Sai. Thank you. One last question from Eduardo Morales. Intelligence versus learning. What is the difference in your opinion?
Well, that's a big question. I mean, like, we can spend all evening on this. So let me start with a basic principle. I want to give you a thought. Actually, a colleague of mine had come up with it, but it's such an interesting phrase that it's stuck in my head. I want you to distinguish between deep learning and deep thinking. So deep learning is about a student who is being trained by a teacher. There's, of course, unsupervised learning also, but there's this process by which something is building skill. And deep thinking is about using the skill to solve real-world problems or any type of problem. And so you might think about deep thinking as really the space of intelligence, and deep learning being more pertaining to learning. Obviously, you could be using what you've learned so far to solve problems even as you're doing more learning. And you're probably familiar with reinforcement learning, bandit problems, and so on, where this paradigm shows up, exploration versus exploitation, and these ideas show up. In other words, if intelligence is about deep thinking, using your skill today to solve problems, learning is about improving your skill. And this is the distinction one would draw between the two. But to think about the underlying stochastic process, both are similar. If a robot has learned and goes out there to decide how to take observations really well so that it can tell you what's happening in the world with as little energy consumed as possible, it's perhaps, you could say, it's doing deep thinking. But if the robot is learning how to do control, how to do trajectory planning, even as it is solving the other problem, maybe it's deep learning as it's doing that. But the system theoretic problems are nearly the same. We have the same system dynamics and optimization cycle that are influencing both. So I would say that perhaps that might be a reasonable answer to your question. I don't know if that's convincing to you, but that's how I would answer it.
Perfect. Sai, I would like to thank you. Back in 2013, when I first met you, I was very amazed by how you were able to bring new ideas. You showed us how to work with mapping of coherent structures using unmanned aerial systems, digital fabrications, and fab labs. Thank you very much for bringing us this new idea, this new approach for learning. This is a radically new way to do it, and it's something that we should learn more about. Thank you very much for your talk today.
Thank you so much. And if one thing that happens as a result of this is we can remove the forward-backward iterations and backblock with a parallel distributed update that can use CUDA cores in a different way, we might be able to scale learning even more. And that's what we think we are seeing, even when we are, as we can quantify uncertainty to decide which parts of the networks are more interesting than the others. What did it learn? Is a concept hard to learn? All of these questions now become tractable to us. And I hope you're as excited by it as I am.
I am very excited because backpropagation currently is the foundation for all the learning paradigm that we're using.
That's
Thank you very much.
Thank you so much. Okay.
Gracias a todos ustedes también por su asistencia a este seminario. Este es el último seminario que tenemos este año. Nos vemos el año próximo, el 12 de enero, me parece. 12, 14 de enero, el martes que cae en esa semana de enero. Gracias por su asistencia, que tengan felices vacaciones y que regresen con mucha salud al nuevo semestre, nuevo año. Gracias. Sai, thank you very much.
Thank you so much. Bye-bye.